Hello students, today we are starting chapter 9, Stability Characteristics of Control System. So as you are aware, with, up till now we have discussed about the section 1 on process dynamics, then we started a section 2 and we have started discussing on process control. Now these last 3 chapters are a part of the process control where we are going to study about the stability of the control system. Stability is a very important word because for the design and analysis of the control system, it is very important to know about its stability characteristics. Stability of the control system depends upon the value of steady state gain or sensitivity of controller, and therefore to design control system the stability of the control system is very important. You are supposed to know about the stability characteristics. So first of all we'll discuss what is meant by stable and unstable system, and then we'll discuss about the characteristic equation. Generally, first order and second order systems are said to be a inherently stable system. Generally these are called as a stable systems. Actually, the problem of stability in the control system arises from the third and more complicated systems. So if the order is third or more order, then generally system is said to be a unstable systems. A control system is said to be stable if output is bounded for all bounded inputs. System is said to be a stable system if output is bounded for all bounded input, whereas a control system is said to be an unstable system if output is unbounded for all bounded inputs. A bounded input is a function of time and is always remain within a certain limits during the course of the time. For example, the step function and sinusoidal function, these are bounded inputs because it remains in a certain limit, whereas a ramp or a linear function is called as a unbounded input. Have you understood? So first of all, input should be bounded for the stable system. If input is unbounded, system is never been a stable system. In case of controller, if response grows continuously rather than decay beyond certain value of gain or sensitivity, system is said to be a unstable. So this is one more definition of unstable system, that the response is grows continuously. About the characteristic equation, okay, we will discuss about the block diagram and then we will discuss about the characteristic equation. So this is nothing but the block diagram that we studied earlier. C, U, R, B, then transfer function are GC, G1, G2 and H. What will be its open loop transfer function? Open loop transfer function is a product of all the transfer function in the loop when loop is disconnected at the comparator. So first of all you have to find out the open loop transfer function, which is a product of all the transfer function GC, G1, G2 and H. So G of S is equal to this GC, G1, G2 and H. We can write G of S is equal to G into H. Then you can write the characteristic equation for given control system is 1 plus G of S is equal to 0, where G of S is called as a open loop transfer function. So this is a character equation. 1 plus g of s is equal to 0, and we are going to take this equation as a basis for finding the Routh-Hurwitz stability criteria. So before that, we will discuss about the graphical representation of stability. The location of roots of character equation on the plane determine the stability of the control system. This is a graph. Okay, the location of roots on this graph or plane determine the stability of the control system. So this is the real axis, is a imaginary axis. There are 4 quadrants. You know, it is roots are a1 and b1. The second quadrant is a1 and minus b1. Third quadrant minus a1 and minus b1, and last fourth quadrant is minus a1 and b1. So the right side is of the imaginary axis is to the right and left side is to the left. If the roots of characteristic equation lies in the right side of the plane, means that is of the imaginary axis, the control system is unstable and the roots having positive real part. If roots of the characteristic equation lies in the left side of the plane, the control system is said to be stable system and the roots having a negative real parts. So there are two things. When the roots are to the right side, system is unstable. When roots are to the left, system is stable. Second one is, if the roots of this characteristic equation having a positive real part, system is unstable. If these roots having a negative real part, system is stable. If the roots of characteristic equation on the imaginary axis of the plane, then the system is on the verge of instability. If roots of characteristic equation is on imaginary axis, is it right? Then system is said to be on verge of instability. So we will discuss about the Routh-Hurwitz stability criteria, which is the first method to discuss about the stability characteristics. Routh-Hurwitz is nothing but the algebraic method which is used to determine the roots of characteristic equation and the stability of the system. This method is used for only a polynomial characteristic equation. So you will know why it is used only for polynomial functions. So in this case you have to write the characteristic equation of the control system. 1 plus g of s is equal to 0. Then this characteristic equation is written in this following form: a naught s raised to n, a1 s raised to n minus 1, a2 s raised to n minus 2 plus a3 s raised to n minus 3, and this will be continue up to plus an is equal to 0. So n is number of roots of characteristic equation. A naught, a1, a2, an are the coefficient of characteristic equation. So this a naught, a1, a2, a3, these are called as a coefficient of equation. Okay. If any coefficient is negative, now this out of a naught, a1, a2, an, if any of the coefficient is negative of the characteristic equation, then system is obviously unstable. Now if the coefficients are positive, then system is stable or unstable. So if the coefficients are positive, all coefficients are positive, system is said to be stable or unstable, then it is necessary to apply the following procedure. First of all, you have to arrange a Routh array. So Routh array is arranged into first two rows. So it can be written as equation row 1 and 2. All these coefficients are written in alternate way: a naught, a1, A2, A3, A4, A5, A0, A6, and after that the value of B1, B2, B3, C1, C2, C3, D1, D2, E1, E2 and F1 is find out. How it is find out? So this is nothing but the equation which is used to find out value of B1, B2, B3, C1, C2, C3. So B1 is equal to what? A1, A2 minus A0, A3 upon A1. What is B2? B2 will be A1, A4 minus A0, A5 upon A1. So thus the elements of the remaining row is find out and route array is arranged. Now the following theorems are used to determine the stability of the system. So what are the different theorems? Then theorems of the Routh-Hurwitz test is if all the elements of the first column of Routh array means A0, A1, B1, C1, D1, E1 and F1 are non-zero and positive, system is said to be stable. If the roots of character equation having a negative real part, system is said to be a stable system. If any element of first column are non-zero and are negative, that then this indicates that one root of the character equation has having a positive real part and system is unstable. The number of roots with the positive real part is equal to number of sign changes for the unstable control system. If one pair of roots is on imaginary axis equidistant from the origin and all the other roots are in the left side of the plane, all the elements of nth row will vanish. And the location pair of imaginary roots on imaginary axis can be found out by solving equation cs square plus d is equal to 0, where c and d are nothing but the element of the array in which n minus 1th row reads from left to right. There are many limitations of Routh-Hurwitz test during stability calculations. Routh-Hurwitz test is only used for polynomial functions. It is not used for exponential functions like transportation lag. What is nothing but the equation for transportation lag? It is e raised to minus tau s. So for such equations, Routh-Hurwitz test is not used. It provides the information about the stability of the system but does not give any information about the degree of stability. It also not gives the actual location of roots on the characteristic equation of the plane. So this is how we can study Routh-Hurwitz test for calculating the stability. So this is how by applying this conclusion you can find out system is stable or unstable. Now we will discuss about some problems related to the Routh-Hurwitz test. The first problem is problem 9.1 is to write the characters equation and the construct the Routh array for the control system shown in the figure. And it is asked, is the system is stable for kc is equal to 9.5, kc is equal to 11 and kc is equal to 12. So this is the block diagram kc 1 upon s plus 1 into 0.5 s plus 1 and the measuring element is 3 upon s plus 3. So the transfer function g of s is equal to kc upon s plus 1 into 0.5 s plus 1 into 3 upon s plus 3. It is a product. Open loop transfer function is a product of all. 1 plus g of s is equal to characteristic equation. So 1 plus g of s you can write like this. You can solve it, and for kc is equal to 9.5. What you can do? You can make the calculation and you can find out the equation which you can arrange into a route array. So see here 0.5, 3, 5.5, 31.0. This is how you have to arrange the route array, and from this you have to make a calculation to find out value of b1. Once you find out value of b1, okay, for kc is equal to 9.5, all elements of the first column are non-zero and positive. System is said to be a stable system. Equation 3 becomes when kc is equal to 11. This is the equation, and you get 0.5 s cube 3s square plus 5.5 s plus 36 is equal to 0. Again this is arranged in a first two rows. See 0.5, 3, 5.5, 36, and then value of b1 is find out. b1 is how it is found out? Cross multiplication. 3 into 5.5 minus 36 into 0.5 upon 3. You can find out b1 is equal to 0.5. Means what? If kc is equal to 11, one element of the first column of route array is negative, therefore system is unstable. If kc is equal to 12, okay, again you can put this value of kc into the equation and you will get the equation 0.5 s cube 3s square 5.5 plus 39 is equal to 0. Again this route array can be arranged alternate manner 0.5, 3, 5.5, 39. You can find out b1 value, it is minus 1.3. So if kc is equal to 12, the third element of first column of route array is negative, therefore system is unstable. So this is how you can solve any equation related to the Routh-Hurwitz test, so that you will get the stability characteristics. So we'll discuss the remaining into a next lecture. Go through the book, start reading, understand the concept of stability, Bode diagram, root locus and route array, and then go for solving the problems. So in next lecture we'll solve one more problem and then we'll go for the root locus diagram.